It's my great pleasure to introduce Matthias Minder and Frederik Steiner from SBB, two machine learning engineers who are going to talk to us today about occupancy detection in their trains. Welcome.
Thank you very much.
Welcome also from our side. We were pleased to present you the SBB Occupancy Forecast today. I guess every one of you has probably seen those pictograms, let's call them by the Swiss German name, the Töckelis. Yeah, so these are the famous Töckelis that has everyone seen, and today we're going to talk about how they come about and what they actually mean. Does anyone in this room actually know what does two Töckeli actually mean? So in the end of the presentation you will know it. But I think, small hint, this room is definitely three Töckelis. So yeah, let's call about our landscape or how this model takes place into in the SBB. So you need to distinguish there are actually two models. One is the class-specific forecast, and the second one is the wagon-specific forecast. So there's two different models, and yeah, they're different. They have their different applications. One is the planning of rolling stock, and the super saver tickets for the class-specific forecast. So we need to plan where the people on the train, that we have enough rolling stock, or that we don't sell super saver tickets where there are too many people. And as well, it's customer facing, so you can see it on the SBB website or in the SBB mobile app. And the data also gets published to open data, so if you want to play with it, yeah, you can go ahead. Another maybe not so obvious thing is the emergency handling. If, for example, if there's train cancellations, the people working with the emergency handling, they need to know how many people are actually on the train to like order replacement buses and such, and hence they need these numbers. And then for the wagon-specific model, it's mostly customer-facing, so people know to control the passenger flow. Like we have 400-meter-long trains, and not everyone should get into the train at the same spot. So we try to guide the people, distributed them equally through the platforms, and it would work if probably more people would look at the forecast. Yeah, that's what about the system. So now, how does the process actually look like? So yeah, as we said, there are two models. One, the class-specific model, takes some inputs that puts out some numbers for a specific train. Let's say we have 189 people on the first class and 520 in the second class, and this gives us the Töckeli. And this then it gets put into the wagon-specific model, and we distribute these people onto the train. Now, we closely work together with the business. For example, they work with our numbers, as we said before. And if there's, for example, a event such as the street parade or whatever else there is, they can manually override our prediction if they're not convinced that, or they think that there will be more people in the train. And hence, yeah, what do we have? They override the predictions. We have more people on this train, and also this gets put into the wagon-specific model, and we have more people also in the wagon-specific case. Now, about the data. So we need to predict actually for each section. We need to do a prediction. So a section means between every stop we have an actual, or we need to give an actual number how many people will be on this section. So a section is one step stack between one and two stops. So for this we need some ground truth data, and there we have with the long distance services we have manual counts by the train crew. Maybe you have observed them once or twice where they just walk through the train, and some people even have a clicker where they count the people with that. Next time you ride the train, you need to check if they do it or not. And with the regional services, we have sensor data counting the people getting in and out of the doors, and we then calculate these and distribute it on the wagons. Now, for an example, here this will be a visualization, but first of all, I need to talk a bit about it. On the left-hand side, we have a normal first day in May, so 2nd of May. And here's the Ascension first day, 1 week later. And this will be showing the passenger flow on these 2 days when people traveling from Basel or Zurich in direction of Ticino. And what you might realize that there's a lot more people going here on Ascension Day to Ticino than on the regular first day. And now, yeah, you can basically see here there's a lot more traffic going here. And that's part of our data. And I think I'll hand over to Matthias for the next part.
Thank you very much. So now we see like basically the complexity, and we have to predict this in the future. So we can see, behavior is very different depending on the day that we have, on the day type. There's a whole bunch of interactions going on. So let's talk about the model. But before talking about the model, let me briefly take some time to talk something I consider also to be very, very important, and that is the metric. So how do we measure how good a model actually is? And we actually spend a lot of time in this because we want, again, like the most important thing for us is trust. If the business experts don't trust us, they won't use our numbers and we don't have any effect. If you don't trust us, you say, oh, Töckele are always wrong, you're not looking at them and they don't add any value whatsoever. So we really had to build trust, and in order to do this, we incorporated the business in our decision of the decision metric, precision metric. So the question here is, again, how do we decide if a model A is better than the model B? And we want to find a number such that if this number is better for model A than for model B, that the business experts would also agree that model A is better. And since we predict the amount of people, so we predict directly how many people there are, so there are a couple of choices that we could make. We could work with the absolute error, the percentage error, etc. And we don't just want to make this choice, but we want to, make an informed decision. And to make this informed decision, what we do is we look at specific sections. So we have some sections which are quite easy to predict, such as these here. The distributions are quite close together, and there are other sections, as this one down here, where people just do random stuff. And we want our metric to kind of reflect this. So we want, on a very hard section, if our model is off by a couple, like 10, 20, 30 people, it shouldn't penalize the total score too much. Whereas on an easy section, our model has to be sure. And so we validated this with a bunch of different sections, and we have finally found that the mean Poisson deviance is the way to go. And since, the mean Poisson deviance, if I go to the business and tell them, hey, we're using the mean Poisson deviance, they're not gonna be very excited about it because it's very hard to interpret. But since now we have told them why we use it, they actually trust us, and we can just show them plots with the mean Poisson deviance, and they work with this as if they've always have known it. So now we've chosen our model, our way to measure the model. Now let's talk about the model itself. We use LightGBM. Why? Because it's very easy to train. It has only few hyperparameters that we have to tune for it to get to work. And for those of you that are very disappointed that there's no Gen AI involved, well, it's not. Using neural networks for this problem, it's not that obvious what we should do. I mean, you would think that, for instance, graph neural network would be a good choice, but actually we have different graph topologies every day because the timetable changes every day. Or we tried to work with recommender systems, and this has kind of worked, but not as good as LightGBM and not as robustly as LightGBM. But LightGBM doesn't just work out of the box because we have some, modeling challenges. For instance, we have a lot of categorical data. So every train section, so Bern-Zurich is a category. Then we have Bern-Olten is a different category, Olten-Zurich a third category, and this for all 2,000 sections that we operate on in the SBB network. So we already have 2,000 categories for this. Then we have, different date types. That adds another 7 categories. Then we have public holidays. We have to consider them all separately because Ascension is very different from Christmas. And very quickly, the amount of dimensions in our model blows up. And even worse, we have a lot of interactions between those categories because different sections will react differently to different situations. So in order to address this, we have to do embeddings. So we have to calculate an embedding, for instance, for our sections. We do this for all the categorical things, but I'll show you the section example. So how do we do this? We start from our data on top right, and we aggregate it into some kind of, I call this a fingerprint for every section. So we have, we just aggregate for every weekday and departure hour, we calculate the median of the amount of people on this train. And this gives us a fingerprint. It shows kind of like a curve. What does a typical week look like on this train? And we on this section. And then we do this for every section. And since those, those fingerprints are very, there's a lot of correlations in them because, we have the morning commuter sections, we have the evening commuter sections. And so we can reduce dimensionality quite a bit. And we do this with PCA because, it works. It's very, very robust and no need for fancy stuff. And we end up with 3 principal components, which actually already suffice to categorize or to characterize how a section behaves. And what do we end up with? Well, first, it looks a bit like a mess, but then we start to see good things. So basically, what we want to see here is that sections that behave similarly are also close together in the embedding space. And we have some indices that this works. For instance, we see Wiel, Frauenfeld, and Winterthur, Frauenfeld, Winterthur, Wiel. Those are 2 sections in the same geographical region with similar behavior. They're close together. That is a good sign. Or also, for instance, you see Zurich-Bern is a very extreme section, which is kind of like nothing else, as you probably know if you commute between Zurich and Bern. So it's really far apart from everything. But that's not only the only interesting thing. Another thing that we observe is that actually there seems to be some mirroring effect. So if you look down here, for instance, you see Bern-Thun is down here, and the opposite, like the same section, but travel in the opposite direction, is very far up there. The same thing for Zurich-Olten, Olten-Zurich. And you see this everywhere, Geneva-Morges, Morges-Geneva. And so actually what happens here, it's very interesting to us because this second principal component seems to capture the fact whether it's a morning or evening commuter route. And the more extreme the commuter behavior is, the further away we are on this axis. So actually, just from our data, without any a priori knowledge, we can identify whether some section is used more by commuters and whether it's more, attractive during the morning and the evening. And then the third principal component, I don't show this here, but basically it captures the same thing for leisure traffic and whatever happens on the weekend. So now we have good embeddings, we have a good model, we can make predictions, and let's look at the same example as before. Again, on the left-hand side, a regular Thursday, on the right-hand side, Ascension. And let's look at our predictions. And you can see, very early in the morning, nothing is happening. But then people want to go for their gelato and Ticino. So people are very strongly traveling to Bellinzona and further down to Lugano. Whereas, on this other side, you can see that, on a regular Thursday, there's not that much affluence going to Ticino. And then you can see towards the evening, you can see commuters going home. So those are the people that commute home from Ticino. So there's a bit of a stronger signal on a regular Thursday towards the evening. But we're good, but we're not perfect, again, as you probably know. For instance, if we look at this plot, this is the performance throughout the year 2023. And we see very prominent peaks. And if you look into your calendars, you can probably figure out why this is. We have the 1st of May, we have Zürichfest, Street Parade, and Bahnerfahrt, which really mess up our prognosis. And this is actually, such events are actually very hard to model because, for instance, Zürichfest only is every 3 years, so we don't have that many examples of this happening. We have other events like the Eidgenössische Schwingfest, which is in a different place every 3 years, so that's even worse. And also the behavior during events really depends on the weather and like other factors. And for instance, this 1st of May thing, that's not people going to protest, but that's people profiting from their long weekend, because actually on this year, it led to a prolonged weekend and everyone again went to Ticino. A second thing we're struggling with is the weather, because, well, this might be disappointing to you, but actually the weather wasn't that much of a priority since the real business case is in making very long-term predictions, because that's where we still can make changes to the train composition, and also that's where when we start selling the Super Saver tickets. So weather wasn't a priority, but then we still tried because, I mean, we kind of have to. But it seems like it's just one interaction too much, because, not only have different, sections, weekdays, but then also you have different behavior on the different seasons, and depending on the season, people don't really care whether there's snow in April, but they care about snow in February and stuff like this. So there's just too many things happening, and in practice we see a lot of overfitting right now. We're working on it, but we haven't got it to work yet. So yeah, that much for the model. Now I'll hand back to Frederik, who's going to talk about how we, ensure that this actually works.
So yeah, since we're a productive model, and we train our model every week, we need to make sure that we deploy something that's actually working and that we can trust in, and the business also trusts in. So for that, we deployed some quality assurance. One of those is model probing. In this case, we had a lot of discussions with the business experts to check, to make some toy examples, to give the model and make predictions and see if the model does actually something useful. For example, we have a commuter route and we check whether the predicted occupancy is higher at 7 on a weekday than at 11 on a weekday. And same goes for leisure routes. We predict the occupancy on a Saturday or on a Wednesday and check, hey, does the model predict actually something useful there as well? Yeah, that's just that we can sleep better and the business also sleeps better when we deploy a new model. Another thing that's more for our side is we have a lot of plots implemented. One of those is Shapley values, or we plot partial dependence plots. Here we have a partial dependence plot of the halbe Stunde, so the departure half hour, and the expected prediction and here we can clearly see the trend that we expect, like a peak hour in the morning, and afterwards in the evening there's another peak. And yeah, that's for the data scientists, that we can check the model as well and see, hey, is it something useful? So now, before we go to the questions, I have to still tell you what does it actually 1 töckeli mean, or 2 töckeli means, or 3 töckeli means. So 1 is between 0 and 50% of occupancy, and then the 2 töckelis are between 50 and 80% of the occupancy, and yeah, 80 is 3 is from 80 onwards, and however many people you can cram into the train. Yeah, that was it with our presentation, and yeah.
Thank you very much. Thank you.
Thank you.
You certainly managed to occupy this room very well. So, questions, please. I'll just start here.
Thanks for the talk. It was really cool. I have a question about the reaction of whether you have to model also the reaction of the people to the prediction. For the wagon occupancy, like if you say the front of the train is going to be super full and the back is going to be empty, if everybody's like, oh, looks like the töckeli is like, oh, let's all go to the back. Like, this is extreme, but in general, do you have to model this? Do you do that?
It's a very good question, and that's the question that also keeps me up at night. But basically, right now, what we see is that, so we don't do it. We don't do any kind of correction like this. This kind of model, the models that we use, they have some tendency to be biased towards, some mean. So maybe there's also already an implicit, correction going on in this, but also we don't people don't look at our things enough for this really to have a very strong effect. But yeah, we have to. If you have a good way to actually do this, come towards me, because it's really non-trivial, I think. Yeah.
We have another question.
Yeah.
So coming to the assurance part, how do you make sure that your probes do not filter to the people training the model, so that they train biased by the probes you're going to use?
I think I can answer this. So what we did is it wasn't us that chose the prompts, but it was really the prompts, the probes, but it was the train experts. So they're really like we went to them to really the people that it's their daily business to manually predict this occupancy, and we asked them, okay, so what do we really have to get right? And if we don't get this right, we have to like immediately trash our model. That was so it wasn't our bias that we introduced, but it was in close collaboration with the experts that we did it.
But then you could train for these probes, right? So you could train the model to be good at those probes and nothing else.
But those probes are just not our primary training objective. We still, look at the overall mean Poisson deviance, and we also make sure that we have an overall good performance. But the probes are really like you can think of it as if you were to deploy a model that does automatic driving, then you would also introduce a probe that, if some accident happened in the past and the car crashed, you never want to make this mistake again. And that's kind of a bit of our equivalent, I think.
Yep.
Hi, very interesting talk. Thank you. I was hoping you could tell us a bit about the technology, about the architecture you use, about what it runs on, and also maybe a little bit about the size of the data. You mentioned 2,000 segments. I'm trying to imagine how many times a day, how many trains, how many data points, how big is the data, and how often do you train and things like this?
Yeah, so we have like, maybe Sven can even talk better about how the infrastructure looks like. But yeah, we have just the company-wide infrastructure that is there for enterprise analytics. And yeah, there we have Snowflake database and then Argo CD and Kubernetes clusters and whatever there is. And yeah, and we have something like and MLflow and modular repositories and that stuff. Basically everything you need there is there. And
and for the amount of data, I think, actually I don't know by heart, I think we make 60,000 predictions a day. So, like we have 2,000 sections, and on every section you have every half hour a train typically. And we have data going back to 2017, but we see also that all data prior to Corona we can throw away because people now travel differently. With the home office, actually using the more data hurts us, which is I find very interesting.
Thank you.
Thank you very much for the presentation. Very interesting. It's a topic that's close to everyone's heart, I guess. So I have a question regarding the modeling. So you mentioned that the main target is to predict longer term, so to be able to adjust also what the trains do. But I'm wondering then, when it gets to shorter term, when I look at it on my app, the train is already in motion, so the sensors already have some data. You already know based on real-time information what actually is happening. Is there some interaction between this real-time data and then the forecast I am shown on the app?
No, there isn't right now, and also it's kind of actually harder than you would think because you don't care about how many people are in the train right now, but you care about how many will be in the train with you. So especially for like large, long-distance trains, there's so much exchange. For instance, in Bern, there might be 300 people going out and another 400 coming in. So it's not completely obvious to use real-time data actually. And so what we could do is look at how many people traveled in the morning and then, try to predict how many people will come home in the evening. That we could do. But the business case for this isn't actually that strong. So the fact that you see this in the app is kind of a side effect. I'm sorry to tell you, you're not our priority right now. So yeah, I think that's the answer.
Do we have a quick last question?
You mentioned that you do this also for regional trains, but regional trains are very often operated not by SBB. So does it apply to those other 254 roughly travel companies or as well, or only SBB trains?
Currently only SBB trains, but I don't know. We're in talks with other companies if they want to adopt or take prognosis from us, but yeah, that's not officially or anything decided yet.
Thank you very much.